Yeah, good morning, everyone. This morning, I'm going to be talking about what we call nitrogen and its compounds. Therefore, we're going to be picking them one by one. As we know, I always like to start with the symbol of this particular nitrogen. Nitrogen is a gas, therefore, you see it as N2 in any chemical reaction. We call it the atomic gas, and aside this, you can get them in the atmosphere, taking about 78% in the atmosphere. Taking about 78% by volume in the atmosphere. Basically, we know we can equally find it in a combined form as sodium nitrate or sodium nitrites. You can have it as NO3, or you can have it as calcium nitrate. And you equally know that nitrogen helps in the atmosphere to reduce the amount of oxygen that will have gotten to us, therefore making it was reasonably enough for us to have oxygen that we need in the atmosphere. If nitrogen is not there, a lot of oxygen will have gotten to us and affects what we do around us. But with the presence of nitrogen in the atmosphere, that helps reduce the amount of oxygen that gets to us. We equally have them in protein, the food we eat, especially talking about the protein. We have these nitrogen proteins, and we can find proteins in our body. Therefore, we can find this protein in our body, and our body use this particular nitrogen found in protein to build so many things in our body. We use it to build muscle. Not only that, we use it to build our bones. Not only that, skin. Not only that, we use this to build so many things and other tissues in our body. In fact, we need to know that it's taking about 3% by mass of our body. Therefore, nitrogen is so important, as we know. You always see them as N2. I always have them as 98% in the atmosphere by volume. You can have them in a combined form. You can have them in the full heat. Then the body as proteins, and the body uses these particular proteins to build muscle, bones, scale, and even take about 3% of what by mass of the body system. Therefore, when we're talking about nitrogen, actually forms about 78% by volume. You can have it in a combined form as sodium nitrate or calcium nitrate. You can equally have it in protein our body, which we use to build muscles, we use it to build bone, our skin, our hair, blood, then other tissue. In fact, actually take 3% by mass in our body. Therefore, how can we prepare this particular nitrogen in the atmosphere? As we know, nitrogen can be gotten from air, and air is a mixture of different gases. Therefore, if you are to prepare nitrogen, nitrogen is taking 78%, oxygen is taking 21%, carbon dioxide is taking about 0.003%. So therefore, we have to look for a way of removing CO2 and oxygen from the air. And for us to do that, like CO2, you can use caustic soda. You can use caustic soda. If you use sodium hydroxide, pass it towards CO2, automatically you get it to remove sodium carbonate, solid. Aside this, or use lime water, which is quick lime. You use calcium hydroxide. You use calcium hydroxide as well. Then CO2. Automatically, we get to remove solid. Therefore, we can trap carbon dioxide in this particular form. Then aside this, how will you now remove oxygen? For us to remove oxygen, you can remove oxygen by passing it through a heated copper tuning. You have a heated copper, a very hot heated copper, and then you pass it through oxygen, get oxidized to copper oxide solid. In this case, you trap it or use alkaline power or use alkaline power. Can use alkaline or alkaline power or therefore here what we use there basically we use copper tuning, a heated copper tuning as we have heated copper tuning here. The heated copper tuning will absorb the oxygen for what we call copper oxide. And aside it, the real nitrogen side. Now the nitrogen itself is less dense than air. It's less dense than air and it's not extremely soluble in water. Therefore we can pass it through water. And you see the bubble coming out. We can pass it through water. This is what we call upward. This upward delivery. And why it's possible to pass it through upward delivery is because it's lighter than air in terms of density. It's less dense. It's less dense than air. Therefore, basically, we can easily walk past it through and see the bubble coming out. And it's passing over water because it's not extremely soluble in water. Therefore, this particular nitrogen octane here is very, very pure, taking about just 1% in pure or rare gases as impurities. Therefore, it is even denser than pure nitrogen. When I say denser, it's heavier little than pure what? Nitrogen. Okay, this is the way of preparing nitrogen from air. Not only that, there are different ways in which we can prepare nitrogen. We can equally prepare from ammonium dioxonitrate 3. Let's say ammonium dioxonitrate 3. What can you say? There is ammonium is NH4 diazonitrate. Yes, there was what nitrate 3, which yield what we call a pure nitrogen. And you need to understand that this ammonium nitrite this ammonium dioxonitrate 3, you need to understand that this ammonium dioxonitrate 3 should not be heated directly. And why should not be heated directly is because it is unstable and it decomposes exothermally. When they say something decomposes exothermally, it releases a lot of heat to the water to the surrounding. Therefore, it should not be heated directly. What you can do is to get it prepared from sodium nitrite and ammonium chloride is to get sodium nitrite and ammonium chloride. When you get sodium nitrite and ammonium chloride, ratio 7:4. You heated this can be heated. When you heated this, automatically the reaction is going to form what we call ammonium dioxonitrate 3, which is further decomposed by itself to form nitrogen gas and water. Therefore, what we're talking about here should not be heated directly because it's unstable and decomposed exothermally. Then how are we going to prepare it in the lab? What we do is to get a mixture of, since we needed ammonium dioxonitrate 3, what you can do is you get sodium nitrite and you get ammonium chloride, so that by the time they both react together, they are going to give us what we call ammonium dioxonitrate 3. And this ammonium dioxonitrate 3 will decompose. Basically, we decompose in the solution to form nitrogen gas and water. As you can have it here, by the time both of them combine together, by the time this and this combine together, automatically we have sodium nitrite, which is NaNO2, then with ammonium chloride, which is NH4Cl, this sodium plus this NO2 minus, then this NH4 plus, then Cl minus. Automatically this and this will combine to form what we call sodium chloride. Then this and this will combine together to form what we call NH4 and NO2. Yes, and this will further decompose to nitrogen gas and water. That's all. Nitrogen gas and water, and that will happen. To further decompose, by the time it happens, you are further eating the nitrogen gas. And the nitrogen gas is being collected by what's called upon delivery because it is less dense than air, and aside that, you collect silver water because it's not extremely soluble in water. Therefore, this is water, this is drop, this is what fish, this is shelf, this is what a glass jar that we use to collect the ammonia. This one is another way of what preparing nitrogen aside from air. Then another one is through what ammonium heteroxide what 6 7 this 4 so this 14 okay 6. Then when ammonium heptaoxodichromate 6 is heated, automatically it's going to decompose into nitrogen gas, the chromium salt and water. Therefore, when you eat this, it's going to decompose into nitrogen gas, the chromium salt itself, which is Cl2O3, and water. Likewise, you can prepare from ammonia. This can be prepared from ammonia by using copper oxide. What happened? The copper oxide, what you will have noticed, oxygen has removed. Therefore, removal that is reduced. Copper oxide here, this has been reduced to copper, and that is oxidizing agent. That is what reducing agent. What happened? This has oxidized ammonium to what? Nitrogen gas, and the copper has been what? Reduced from copper oxide to what? Copper. This has been reduced while nitrogen has been what? Oxidized. Because oxidation is removal of what? Hydrogen, while reduction is what? Removal of what? Oxygen away from water. Therefore, this particular reaction is very important. This is a reducing agent. This serving as what? No, this serving as oxidizing agent. This serving as what? A reducing agent. Therefore, ammonia gas is reduced. Ammonia gas reduces copper oxide to copper, while copper oxide oxidizes ammonia gas to what? Nitrogen gas. Likewise, we can equally get it from dinitrogen 1 oxide. Dinitrogen 1 oxide is passed over red of copper, and the gas is reduced to what? Say, the gas is equally reduced to what? Nitrogen. While the copper itself is oxidized to what? Copper oxide. Therefore, when you use dinitrogen 1 oxide with red hot copper, the dinitrogen 1 oxide gets what? Reduced. That's the removal of what? Oxygen reduced to nitrogen gas, while copper is oxidized to copper oxide. The only thing you notice here is water is not formed because there is no there is no hydrogen in the right-hand side. Then how can we prepare it in the laboratory? Fine. For us to prepare it in the laboratory, we use fractional distillation. We use fractional distillation and we need a liquid air. Therefore, the first thing is to remove carbon dioxide from the air, which is what we've done before. We use caustic soda. Caustic soda will absorb the CO2 coming from the air. Then later we liquefy it because we need a liquid air. Then the liquefied air without what CO2 is now subject to what compression, because it is a gas. It can be compressed and cooling process so that we can have the cold air. Then during distillation will happen. Then afterwards compression and cooling process taken to the chamber. Therefore, the liquefied air, which is cool at about minus 200 degrees Celsius, is taken to the fractionation column. And in this fractionation column, as you can see, the nitrogen will come out first. Why? Because of its boiling point. Therefore, the boiling point is minus 190 degrees Celsius, and it's separated from oxygen, which distill later at minus 185 degrees Celsius. And the whole thing is now the oxygen is coming out and is stored in a steel container or cylinders and sold as liquid nitrogen or a compressed gas. Therefore, the successive compression and cooling is very important before taking to the fractionation column. And that is just the process of preparing nitrogen in the industry. That is the industrial preparation of nitrogen. Then the physical properties, the colourless, odourless, and tasteless gas. Talk about colourless. Most of these gases are colourless, but this has no odor and it has no taste. Pure nitrogen is slightly denser than air. Pure nitrogen is slightly denser than air. But the one prepared in the laboratory is not as, it's slightly lighter. Slightly lighter than air, meaning it's not denser than air. It's slightly lighter than air. It is slightly soluble in water. It's not extremely soluble in water. That's why we can pass it through over water. It has a boiling point of minus 196 degrees Celsius and the melting point of minus 210 degrees Celsius. And you will ask me, why is it possible? Because of the van der Waals force that is present in the nitrogen gas. Then nitrogen is in group 5 element which form equivalent bonds in its compound. Nitrogen, as we know that the nitrogen is 7, therefore when you draw the electron shell, automatically on the valence shell, you are going to have how many electrons? 1, 2, 3, 4, 5. You are going to have 5. Therefore, it has 5 valence electrons, which automatically it needs 3 more. Therefore, it needs 3 more electrons. Therefore, when you see it's forming how many bonds? It's forming 3 bonds to form nitrogen gas. You see, because if you draw another nitrogen, here, you're going to have the same thing. Therefore, they can share here, and they can equally share to form this triple bond. This bond makes it very, what will I put it, unreactive, because we need a lot of heat to break down these particular bonds. Therefore, the kind of reaction here is sharing of electron. And for sharing of electron, and for sharing of electron, we call such bond equivalent bonds. It also form ionic bond with group, group 1 and 2, by accepting 3 electrons to form nitride. When you have sodium, which is group 1, it's going to have this sodium, and when you look at sodium is 11, Therefore, sodium needs to lose 1. Then 3 of sodium will come in because it needed 3 of sodium will come in to get you 3 minus, which is nitrogen. And when such happen, what happen? From N, then Ne, NaN3, this is what we call a form what we call a sodium nitride ion. Because this is getting how many? 3. Getting 3 of sodium plus, combining with 1 of what? N3 minus. And when it happens, it's formed. Because the 3 will go to this, the 1 will come to that, the 1 will come to this. Guys, by accepting 3 electrons, therefore it has accepted what? How many electrons? 3, which is 1, 2, 3. To form what we call ionic, this ionic what? Bond. Why is it ionic bond? Because it's transferring electron. It's transferring what? Electrons to nitrogen. Automatically meaning it can form both the covalent bonds, and it can equally form ionic bonds with group 1 and group 2 elements. Then for the oxidation state vary from -3 to +5 in its various compound. You need to understand this particular one. It means it can take from -3. Okay, like we have -3, -2, -1, 0, 1, 2, 3, 4, then 5. Therefore, you can have like every second with oxygen now. With oxygen is 2 minus. Therefore, you can take 1, and when you take 1, you have N2O. This is dinitrogen 1 oxide. You can take 2, that is N2O2. Automatically, we'll be having N2O2, which can cancel out to give you what we call NO. This nitrogen, what we call this 2 oxide. Likewise, it can come with this N3, then O2. Then in this case, the 2 will come here, the 3 will come here to form N2O3. This dinitrogen 3 oxide. Dinitrogen 3 oxide. Then you can equally form N4O2, which is N2O4. And when you cancel this, 2 here, 2 here, 2 here 1, you have N1, 2 here 2, you have O2, which is NO to this nitrogen 4 oxide. Then you can equally have it as 5. And you can have it in hydride when you come to metals, when you're reacting with metals, like sodium nitride, magnesium nitride. Automatically, and I'll talk about this particular one. Very, very unreactive because of the Because of the triple bond I possess, and you need a lot of energy to break this particular bond. However, at high temperature and pressure, nitrogen combines directly with hydrogen, oxygen, and certain metals. So basically, reaction with metals, nitrogen combines directly with very electropositive metals to form nitride. We talk about this electropositive metal. This magnesium with nitrogen to form magnesium nitride. This one has minus. Magnesium nitride. We have Mg2 plus, then N3 minus. Automatically you have Mg3 N2. Yes, then this nitride, when dissolved in water, what happens? It forms the base and ammonia gas. Form the base and ammonia gas. Therefore, it's forming magnesium what? Hydroxide and what? Ammonia what? Gas when dissolved in water. Especially one when you warm this particular what? Product form. That is a reaction with metals. Then reaction with non-metals. When you're talking about reaction with non-metals, okay, when you're talking about reaction with non-metal, nitrogen combined reversibly with nitrogen combined reversibly with what? Hydrogen to form ammonia. That is when you have nitrogen gas combining this way. Oh, sorry. You have nitrogen gas. You have the nitrogen gas combined with what? Hydrogen gas in reversible order to form NH3 gas. Then what happens here? You put two here, then you put two here. This will call Haber process. The nickel temperature about 450 atmosphere to show what is. Therefore, here this will call an Haber process. Therefore, you say what? Nitrogen combined reversibly to form what? Ammonia. Yes. Then with oxygen, it's combined directly at a very high temperature of about, wow, with oxygen you need a lot of what? 2000 degree what? Celsius. 2000 degrees Celsius, because you need a lot of what? Heat to break the bond between nitrogen molecules, therefore to form nitrogen 2 oxide. Okay, that is, this reaction occurs in the what? Atmosphere during lightning. That is what you see during lightning. Lightning what? Flashing. During lightning flashing, what we have is what? Nitrogen combining with what? Oxygen. Because we told you that normally nitrogen reduces the oxygen in the atmosphere to get us reasonable oxygen that we need for our normal day-to-day activities. But during lightning, what happens? Nitrogen combined with oxygen to form nitrogen 2 oxide, and the temperature is about 2000 degrees Celsius. Okay, then we'll talk about the uses of nitrogen. Nitrogen is used in the manufacture of ammonia, cyanide, cyanamide, and carbamide. It's an important fertilizer. Liquid nitrogen is used as a what? Cooling agent. Yes, liquid nitrogen is used as a what? Cooling agent aside of what? Manufacture of what? Ammonia. Then because of its inert what nature, it is used as a what? Gas carrier in gas chromatography. Yeah, we told you that because of the triple bond in between the nitrogen, therefore this inert nature of nitrogen, it makes nitrogen useful in gas chromatography as what? Carrier what? Gas. Then provision of what? Inert condition of certain industrial processes that involve easily oxidizable chemicals. Manufacture of transistors. There is handling of what? Metals. Transistors and handling of what? Metals. Then it is used as a preservative to prevent acidity. Yes, in what? Packaged foods. Aside what I've talked about, manufacture of what? Ammonia, cyanide. Aside that, we talk about carrier gas. We talk about preservation of what? Food. The preservation of food or as a preservative to prevent acidity in what? In packaged foods.